Hi everybody, and welcome to tonight's video where we're going to be talking about linear functions. This is also going to be the first video where we are introducing our new formatting for notes. So as you can see here, I'm going to have all my notes here on the left hand side, and on the right side I don't have a dividing line or anything, but I'm going to leave a bunch of space here for when we do examples. Also, I'm going to have a lot of different colors going on as usual, but the color blue is going to be reserved for writing out examples. And then also if I have something that I'm going to say, but I want you to write down. So whenever there's something that I'm going to say but want you to write down, I'm going to just use an exclamation mark like that. And I'll try to put it in line with what I'm talking about so that when you have in your third column on this side here, where you'll be taking the notes down about what I say, hopefully that'll give you kind of an idea on where to match up with what we're talking about. So tonight's video is linear functions, and this is the first video, or the first chapter I should say, that we're going to spend looking at all of those functions we talked about in chapter 2. So we had that packet of what we called parent functions. Now the next few chapters are going to break those down individually and look at each one one at a time. So today we're going to start with linear functions. And linear functions are written in the form y equals mx plus b, or you could say, since we're using function notation here, we're going to call this f of x equals mx plus b. So this is something that I'd want you to write down. In this case, y and f of x, whenever we see those, they're interchangeable. So you can write that down. The domain of linear functions will always be all real numbers. And remember, there's a few different ways we could write that out. I could just write out all real numbers. I could also write out negative infinity to positive infinity. And that's what we call interval notation. Okay? I could also write out the domain is going to be all x values such that x is an element of the set of real numbers. And that would be set builder notation. And then finally, you could write this as just this boldface R as the set of real numbers or all real numbers. You could also put that R in braces, and you could consider that set builder notation. I think some people would argue that putting the R inside the braces would be redundant, because just by seeing the R, we know that that is the set of all real numbers. That's a symbol for it. But there's interval notation, where you have the endpoints of your interval, either enclosed by parentheses or braces. Set builder notation, where you have an x such that, and then it describes the elements of that x is the set that x is an element of, or you have just set notation. So there's a difference between set builder and set notation. The braces are in both, but for set builder, you're actually describing the set, and with the set notation, you're actually saying what the set is. Okay. So that's a little review of our notation to write out what a domain or range are. Now, the domain is all real numbers for a linear function. The range is going to be a little bit different. So the range can be one of two things. It can either be all real numbers, and that would be when m does not equal 0, right? So if I have some positive or negative number for m in my equation up here, if m does not equal 0, then the range will be all real numbers. But the range will be all y values such that y is equal to b if or when m equals 0. And so all real numbers, that would be m does not equal 0, so I'm either going to have a negative slope or positive slope. And in this case, if m equals 0, that would be a constant function, and that would just be a horizontal line. So slope would be 0. Okay? And as I just mentioned, the graphs of these linear functions will be lines. and they'll either be positive, negative, or constant slope. And so they'll either be increasing, decreasing, or constant. So I have my increasing linear function, a decreasing linear function, or a constant linear function that would look something, the graphs would look something like that. Now, whether or not they are increasing, decreasing, or constant is depending on their average rate of change. And remember, average rate of change is the same thing as slope. So when we're referring to average rate of change, or if you hear me say slope, those are the same thing. So m or slope or average rate of change all mean the same thing. Okay? So now, the graphs will be increasing, decreasing, and constant depending on the average rate of change. We already know that it's increasing if the average rate of change is positive, decreasing if the average rate of change is negative. And remember, we're reading that from left to right. And it would be constant if our average rate of change is 0. So, looking at the average rate of change, there's a few ways that we can determine the average rate of change or slope of a line. We could use our slope formula, y2 minus y1 over x2 minus x1, remembering that the average rate of change is the change of y over the change of x. That's why we would do y2 minus y1 over x2 minus x1. But we can also use a table of values like we have right here to determine our average rate of change. So to calculate, compare the difference of two y values, or f of x values, remember y and f of x are interchangeable, to the difference of two corresponding x values. And so all we have to remember is that when we are comparing these values, that we are using corresponding values. So over here, if I want to determine the average rate of change for the function given the following table, what I would do is I would determine my change of x. What's the change of x between -2 and -1? Well, the change would be +1. I'd be going up 1. Compare that with my delta y, or change in y. The difference between -10 and -5, that's going up 5, right? I'm going up 5. So in this case, I have my delta y over delta x. So delta y over delta x is +5 over +1, and you could simplify that to 5 over 1. Now compare that with any other values. So here, let's compare between 0 and 1. Again, delta x is +1, and between 0 and 5, delta y is +5. So again, I have 5 over 1 to compare my two rates of change, or my change of y or change of x. So that would simplify again to be 5. Now we have to make sure we're doing corresponding values. So it would be incorrect if I tried to do something like this. If I did the change between 0 and 2, that would be +2. And then I did something like this with 0 and 5, that would be +5. What I'm noticing here is that these aren't the same values, right? I jumped over. I did 0 and 2. The corresponding y coordinates would be 0 and 10, right? So make sure that you're always using corresponding values when you're comparing the rates of change. So if I look at this, I can determine my rate of change for this function f of x. So for f of x here, my average rate of change is going to be 5. Okay, so I determined my slope just by comparing the change of y to the change of x for any two corresponding points or corresponding rows in my table. Now, I can also recall that the y-intercept is where the graph intersects the y-axis, or in other words, where the x value is 0. So we can determine the y-intercept from a table of values as well. And that would be wherever we see x equals 0 in this column, the corresponding y coordinate is going to be b. So in this case, just from looking at this table, it's a little sloppy with all of our scratch work on it, but I could tell from this that m equals 5 and b equals 0, just because I've determined my rate of change between 2 points, and then I've also identified the y-intercept because I've identified where x equals 0, right? So once we have m and b, we can write an equation for f of x. So in this case, I know that f of x equals 5x plus 0, right? I could write the plus 0. I don't have to. 5x plus 0 is just 5x. So if I want to determine the equation of this line or this function that's represented by this table, I can do that just by looking at the values. Now, if we have a table and we are trying to check for the average rate of change here, one little note about linear functions is that the average rate of change is always constant. It's either the same positive number if it's increasing, the same negative number if it's decreasing, or the same number which will be 0 if it's constant, right? Because the slope of a constant or horizontal line is 0. So if we're comparing our 2 points here on our table, and we discover that the average rate of change is giving us different rates, then the function that we have here is going to be nonlinear. So for example, if I look at this table and I compare my delta x, right, the change between these two x values is +1, and then I look at my delta y over here, and the change between -10 and -7, that's +3. Okay, so here my slope would be +3 over +1, or my average rate of change would be 3. Down here, if I want to compare, let's say, 1 and 2, again, my change in x, my delta x is +1, but now my delta y is the difference between 1 and 6, and that's going to be +5. So down here, I've discovered that my rate of change, or m, is 5 over 1, which is 5. So these two do not match, so that means that this function that's represented by this table here is nonlinear, right? If it's linear, no matter what m or what slope or average rate of change I pick out from this, they always have to be the same. So in this case, they're different, so that's how I know that this function here would be nonlinear. Okay, so we're going to do some practice problems like this in class tomorrow, where we're going to have a graph, or I'm sorry, a table of function values, and we'll have to determine the average rate of change from that. And then we'll also have to determine what the y-intercept is, and then be able to write that equation as well. And then we'll also be given a linear function in its mx plus b form, and be able to graph that, identify the average rate of change, identify if it's increasing, decreasing, or constant, and be able to identify the the y-intercept as well. So come to class prepared to do that, and I will see you tomorrow.